As an example of a grid-forming converter supporting weak grids, we can have a look at our own backyard in Broken Hill. The Broken Hill area is a particular example of a weak grid with a high level of variable renewable generation. This includes a 52 megawatt solar farm and a 198 megawatt wind farm. In that particular area, if we are to demonstrate the functionalities at a very low short-circuit ratio, we can look at short-circuit ratios that can go as low as 1. In order to support such a weak grid, we are looking at implementing grid-forming capabilities in a battery that's currently being constructed in Broken Hill. If we compare the benefits that we get from implementing the grid-forming functionalities in a battery compared to a simple integration of a grid-following battery, we can see that firstly we are able to improve the system stability in that particular area. So the figures on the left show the response of the system following a disturbance, including a grid-following and a grid-forming converter. We see that when we implement the grid-forming control, we are able to stabilize our system, something that we cannot achieve with a simple grid-following converter. A second benefit that we get from the integration of a grid-forming battery is the improvement in the overall short-circuit capacity and the improvement in system strength. An additional benefit we get from the integration of a grid-forming battery is that we are able to increase the amount of renewable energy we can host at that particular area. So the introduction of a grid-forming battery allows us to increase the amount of renewables we can host in that particular area by up to 70 megawatts. The specific outcomes at different locations around the grid can vary because of different factors that can include the specific control implementation of the grid-forming battery, the system strength at the particular area that we are investigating, the number, the size, and the different technologies of IBRs that are locally connected, and even the level of details of the models and the accuracy of the models that we have available for us to do this kind of studies. Grid-forming converters only look at one particular time scale for the response and the operation of the power system. However, we need to take a more holistic view and consider multiple time scales that we encounter in our power system, from the very fast ones to the very, very slow ones. We also need to start paying attention to intraday variations. Because of different solar, different wind generation throughout the day, we now have to manage a system that continuously changes throughout the day, something that we did not have to do when our synchronous generation was coming from coal-fired or gas-fired power stations. We also need to consider how we better choose and how we better optimize the parameters in order to get improved responses from the more and more power electronics we introduce into our power system. This means that we cannot just install our systems and let them run for the next 20 years. We have to continuously review and continuously revise the way that we operate them in order to make sure that our systems remain optimal. Another important challenge is that our power electronics are not synchronous generators. This means that we cannot get the high amount of fault current that we are used to having in our power system in order to have the protection operating the way that we expect it to operate. These current limitations of grid-forming converters is one of the biggest challenges we have as we move towards power electronics-defined power systems.